Kind of like I think the other presentations, this is very open forum, so feel free to just kind of jump in if you need clarification or if I'm saying something that doesn't make any sense. But hello, for people that don't know me, I'm Zach Stoll. I work down in the Brackish Groundwater Desalination Research Facility. We call it BGNDRF. Mike would argue it's called Bergendorf. I think he's wrong. But down in Alamogordo, New Mexico, part of the Bureau of Reclamation. And so, yeah, as the title suggests, we've been hit with this lovely PFAS bug. I think we're trying to make lemonade out of lemons, as my manager would say. So here's kind of the story of it. So just real quick, what are PFAS? Very briefly, they're per and polyfluorinated alkyl substances. That's the acronym. And then the two big flavors are PFOA and PFOS. And I'm not going to try to pronounce those for anybody. But there are, I believe, over 6,000 or 6,500 different types of PFAS compounds. They come all in all different shapes and sizes, but these are by far the two biggest ones. I believe they were initially manufactured by 3M back in the 70s or the 60s or maybe even the 50s. Only a couple decades after that, Dow DuPont had purchased those rights. And so they're now the largest manufacturers. It's actually a spinoff now, Chem Kemers, I believe, out in North Carolina. And so if you read anything out in the news about the Cape Fear, there's quite a bit of litigation going on out there with them dumping these PFAS compounds into the surface waters there. And so, they're very attractive because of the way they're chemically engineered. Can you see my mouse? Is it?
Yeah.
Okay. So this is PFOS, and what we're looking at is just kind of a chemical structure. So there's a carbon at each one of these kind of intersections. And so there's 8 carbons here. So 1, 2, 3, 4, 5, 6, 7, 8 carbons. And instead of being a traditional hydrocarbon where you've got it saturated with H's or hydrogens, it's saturated with fluorine compounds. And the fluorine carbon bond is probably one of the strongest bonds, I think, in organic chemistry, or maybe most of chemistry. And so it makes this compound extremely, durable. And it gives it a lot of unique properties. And so just used everywhere. So you can use it in food packaging. And so they spray this stuff on the inside of microwave popcorn bags so that the oil doesn't seep through the bag and get all over your hands. You can use it. It's manufactured as Scotch Guard for your clothes. So you can spray it on your clothes and it adds this kind of hydrophobic water repellents. And I think one of the more common applications is Teflon, right? It's the trade, one of the PFAS, I forget which one, but one of those 6,000 compounds is trademarked as Teflon. And that, that's your Teflon pans. So they're all very temperature insensitive, can withstand a lot of heat, relatively durable, and extremely hydrophobic. And so because of that, they were also used as firefighting foams in one of the big applications is at the Air Force bases. So they'll have their jet fuels and their drills. Well, they'll pretty much light stuff on fire, I think, and then go out there and practice putting it out. And so they've got these huge trucks and then the hoses, and they just spray this stuff down. And it, does really well at quenching extremely hot fires. And then when they're done with it, they just rinse it off and it hits the ground, seeps into the groundwater, and, you hear about it on the news. And so the issues around it, again, because it is so, strong or durable, you get it's very recalcitrant in the environment. But it's also been shown to be extremely toxic at low concentrations, and it's also been shown to bioaccumulate. So not a lot of, you don't want to see these things together, really. It's a lot of difficult issues to overcome environmentally. So that's kind of background on PFAS in general. And so what happened in New Mexico recently? I think we can go back probably as far as 2016 is maybe where it all starts, with the EPA putting out a health advisory. So nothing really enforceable, but it's an advisory for an upper limit of 70 parts per trillion in drinking water. And so that's, 70 nanograms per liter, just about. Sorry, was there a question? Nope. Okay, I'm just gonna keep chugging. And so New Mexico, I think it kind of hit the fan surrounding the different Air Force bases here. So Cannon and Holloman Air Force bases. Again, with those aqueous firefighting foams, they spray it on the fires and they rinse it into the groundwater. One of the big, I guess, stories to break surrounding Cannon was there was a really large dairy farmer out there in Clovis, and his groundwater that he was giving to his cattle was connected to, I guess, hydraulically where they were washing this stuff off into the ground. And so he was one of the larger dairy farmers, I believe, in New Mexico. And his cattle were all tested, or some of the cattle were tested. They found PFAS in the milk of the cows and in the meat. And so this poor farmer's kind of up a creek because of these chemicals, because he can't sell his cattle, can't sell his milk, and now his land's contaminated, so he can't sell his land. And so you can bet your butt there's a lawsuit going on there. And so there were other stories surrounding Holloman. I think a couple dogs died from drinking the water out at the Air Force Base, contaminated with PFAS. Same kind of story. And so on the heels of that, New Mexico Environment Department added the two most studied compounds, PFOS and PFOA, to their list of regulated toxic pollutants. So that was kind of mid 2018. And a part of this kind of, I think, statewide effort involved the New Mexico Department of Health going around the state, and especially around Cannon and Holloman, looking to see how far plumes had spread in the groundwater. And BGNDRF is in Alamogordo, which is about 15 miles north as the crow flies from Holloman. And so kind of in this pursuit of, staking out different, testing different wells around the Air Force bases to evaluate the plumes, they came to our facility. And we've got 4 wells on site, but they only tested about half of them. But then in March, we got the results back, and it turns out we had some PFAS in our well too. And so, of course, they came back and wanted to test the other half of the wells, and they found more PFAS in well 4. And so just to kind of give a spatial idea of what's going on here, this is our facility, just in this kind of square that I'm drawing with my mouse, about 43 acres. And we've got, we're plumbed and designed as a Brackish groundwater research facility. And I think one of the things that's a really benefit for us is we've got 4 Brackish groundwater wells on site that we can provide for testing to clients that come that want to do some R&D. And so you can see the wells highlighted in red are the ones that have PFAS. And we can't figure out the rhyme or reason necessarily how this is the case. So up is north and then down is south. And so, yeah, it seems to be kind of disconnected and where we're finding PFAS. We're not exactly sure how the aquifers are connected or where these wells are tapped in specifically. They are at different depths, but I would expect there to be PFAS here in well 1 as well, but kind of shrugging my shoulders. So, but just real quick, the way we've plumbed our facility, and this kind of leads into some of the issues, is that we take our groundwater from these wells and we pump them to our storage tanks. And then from our storage tanks, we're able to distribute it to the indoor and the outdoor test pads, where clients like universities can pull from this water and run continuous flow experiments and do desalination research. And then they're able to take their waste and either combine and then discharge to our evaporation ponds, or they can take the treated stream and send it to the city, or just send the concentrate to the evaporation ponds. But this is kind of just the general scheme of how we're plumbed. And so if we're looking at wells 2 and 4, what the New Mexico Department of Health found was here's kind of they tested for 16 compounds. Well 2 and well 4 had pretty similar compositions, where it was about 90% PFOA and then PFOS. And then some of these other ones to a smaller extent. I've highlighted the PFOA, PFOS, and then the PFHXS over here, just because those are the 3 that are regulated. So it was originally just PFOS and PFOA, but now they've added this, it's actually a 6 chain, where these are 8 carbons long, so they're bigger. They're a little bit less mobile, easier to remove. These smaller constituents that we're starting to see in these next generation PFAS compounds are getting shorter and shorter chain. So they're more mobile and they tend to bioaccumulate a little bit more. And so, as luck would have it, right coming off of NMED adding these, compounds to their regulated toxic pollutant list, our discharge permit expired. So what do you think happened? Yep, they added PFAS and PFOS to our discharge permit with the other compound, PFHXS. And so, yeah, it's pretty bad timing there, if you will. And so as soon as we heard that, Randy and I hopped in the car and we drove to Albuquerque and had a sit down meeting with some of the heads at NMED about, what are we going to do with this new situation that kind of just got dropped on us. It wasn't really any fault of our own. We don't know if it's from the Air Force Base. We don't think so, but somehow PFAS ended up in these wells. We didn't do anything, it wasn't through any fault of our own, but now we have to comply with these relatively stringent discharge permit regulations. And so out of that meeting came just more or less some directives, if you will. And so what to do and what not to do as per NMED's guidelines. It says, thou shall not discharge any water containing PFAS above 70 ppt to the city of Alamogordo. So that has implications on how we operate the facility. And then we're also not allowed to apply any water with PFAS to the soil that exceeds mass loading of about 1.5 milligrams of PFAS per kilogram of soil. This one we're not as worried about because that's actually quite a bit of water. We do some irrigation studies, but luck would have it, we're actually using a well that doesn't have PFAS for our current irrigation studies. And so looking ahead, it might be an issue, but right now it's not just staring us in the face. So not overly terrible. And then the last thing we really needed to do coming out of that meeting was NMED wanted us to develop a mitigation plan on what we would do if we had accidental discharges either to the city or onto the ground. And I'm kind of rolling my eyes right now, but this was the mandate. So we went ahead and did that. And I'm just going to illustrate, I guess, kind of the thought process here on what we thought would be possible. So Randy and I got back from the meeting, kind of, what are we going to do? And so I'm going to go over kind of how water flows through the facility again, just to kind of illustrate our thought process. And so again, we pump brackish groundwater into our storage tanks, and then we can deliver that water to clients for testing. And again, they most likely discharge the treated water to the city because it's clean, and then the concentrate goes into the pond. And I think the first thing that really struck us was, well, what if we could scrub PFAS from the wellhead? I think that stands out as a good place to start. And so I've got in parentheses here GAC contactors, so granular activated carbon. For those that don't know, GAC and ion exchange are really the only two technologies that are able to remove PFAS effectively that are kind of off the shelf, and you can get them full scale. And so one of the challenges with using ion exchange is that we have brackish groundwater. So, if you have brackish groundwater with salts coming in and you run it through ion exchange, well, you're probably going to change your water chemistry and exhaust your ion exchange resins at the same time. So I think by default, we kind of got backed into using GAC as the PFAS removal technology if we were going to go down that path, which I think we are. And so obviously we've evaluated, what if we put it after the tanks, or what if we treated the concentrate coming from the clients, maybe get volume reduction, doesn't have to be so big. But long story short, we think the best spot is probably up front, just so we don't have to worry about what NMED was really, I think, trying to get at is, if we have a storage tank leak, which we've had before, or if we'd had the concentrate leak out of our ponds from a torn liner, which we've had before, we would have to address those in the future because those would be violations of our discharge permit. And so I think by putting it up at the very front end, we can just theoretically scrub it from the downstream part of our facility and then kind of be done with it. And so based on kind of that thought process, we want to do wellhead treatment, and we're probably going to be looking at GAC. We started some column testing to start probing, the engineering parameters and to try to back out of that some of the cost. And so there are numerous challenges, I think, for us kind of going down this path, because it has the potential to interrupt our operations and how we deal with clients, and I guess more or less the service we provide. But one of the more interesting logistical challenges is, in real life, we think a full-scale system will have to deal with intermittent water demands. And what I mean by that is, when we have clients at the facility, they're not always drawing water. And so there's a really high probability where we might be providing water one day and then have to shut off the system because the client leaves or they're doing something else. And now we're going to have GAC contactors with a bunch of, brackish water in contact with the media just kind of sitting there. And so what are the effects of that really on the GAC and on the equipment? And so have to ask this question of, does GAC scale if it's exposed to well 2 water at elevated temperatures? And what I mean by the elevated temperatures is, so here's our well 2 water chemistry. This is from the summer. You can see that of the 5,600 milligrams per liter TDS, where more than half of it is calcium sulfate. And the calcium species don't really, the divalent calcium species, so the carbonates and the sulfates, don't really like high temperatures in terms of their solubility. So they have the retrograde solubility. And so, at higher temperatures, calcium carbonates and sulfates tend to precipitate out. And so you could think of a scenario maybe where we've got our well 2 water in this, multi-million-dollar system just sitting in contact with the GAC media out in the Alamogordo hot sun at 120 degrees or whatever it is. That could be a recipe for disaster. And so it was just something I think we needed to evaluate. And so I did some quick and dirty stuff. I took Calgon F400, which is a pretty standard granular GAC media. And I took a handful of it, put it in a beaker and set it aside as a control. And so we're looking at an SEM image of that right now. Looks pretty clean. There's nothing on there. And then I took another handful, put it in a beaker with well 2 water, and then stuck it in our oven for a couple of weeks at about 140 degrees Fahrenheit, and then put a lid on that so none of the water could evaporate. And what we get is this. And so same magnifications on the left, again, virgin. And then on the right here, this top right image is kind of blown out, but you can see precipitates starting to form, or something starting to form. And then this bottom right, it's a little bit zoomed in more, and it doesn't look like bacteria or anything. It definitely looks like a crystal of some sort. Wonder what it is. So you can do spectral analysis of this, and shout out to Pei and Wenbin at NMSU for helping out with the analysis on this. This left spectra is just the virgin GAC. So it's mostly carbon, a little bit of oxygen, some alumina and silica. And then Pei's team did analysis on the scaled GAC, and you can see there's a bunch more calcium. There's some sulfur here, or sulfur, and then an increased oxygen peak. So we're getting possibly some calcium sulfate. Looks like a little bit of magnesium, but definitely elevated calcium. So I'm thinking, if it looks like a duck and it walks like a duck or quacks like a duck, it's probably a duck. And so for asking this question, I'm thinking it's a resounding yes. So again, kind of puts constraints on, if we're going to do full-scale treatment of GAC, probably can't have it exposed to elevated temperatures, which again puts constraints on what we're going to do, how we're going to go about building this, and where we're going to put it. So then I think the next logical question is, well, does GAC scale if it's exposed to these high scaling conditions at ambient temperatures? And this leads us into some of the more recent efforts that we've done. So it did some pilot column tests here. And so this is at our facility. It's just normal column. Had some help from our Denver office in designing all the parameters, but just more Calgon F400, standard particle size. We chose a flow rate that would give us a 10-minute EBCT and a 5 meter per hour velocity, which is really standard in the industry. And our bed length turned out to be a little bit less than 85 centimeters to accommodate this. And then again, just the water quality. I think I showed you before, but yeah, we're operating in a pretty tight temperature range because the inside building's climate controlled. And so we ran this for over a year and developed what's called a breakthrough curve. And so on the x-axis down here, what we have is bed volumes. So with these column studies, you don't really think of it in terms of time. You think of it in terms of bed volumes. And then on the y-axis, we have our PFAS concentration. And so you can see from, 0 bed volumes to about 10,000-ish bed volumes probably. There wasn't any PFAS coming through our columns, but somewhere around maybe 13,000 bed volumes, we started seeing PFOA down here sneaking through the column in the effluent. And then over time, it just got higher and higher concentration until we pretty much broke through and all of the all of the PFOA was coming out and none of it was being captured by the column anymore. Probably put this down here. So this is the initial concentration of these 3 constituents. The orange and the gray compounds down here, it's, I think, kind of tough to see what the breakthrough looks like because they're just kind of outmatched, if you will, or their background noise compared to the PFOA concentration. So what we can do is we can normalize, hold on a sec. Sorry, back up a little bit. And so if we're going to look at this in terms of our discharge limit, we have here's our 70 PPT line. So in terms of cost and estimating how much carbon we need and how long we can run it, we're maybe looking at about 16,000 bed volumes approximately before we have to start swapping out this media. And I believe that was around half a year, a few months. And so I'll just go over this real quick. It's the same chart. So bed volumes on the x-axis, but we're looking at the PFAS concentration in terms of C over C naught. So it just gives you a little bit better idea in terms of the relative initial concentration. The smaller chain compound is actually breaking through quite a bit. And the PFOS in the orange is breaking through a little bit, even though it doesn't come through as well on here. So that's all this one's for. And so we did something very similar, evaluating what the carbon looked like coming out of this column after about a year. And so took a scoop out of the column, sent it out for analysis. And so I'll be talking about this, the spectra coming from 1 and then 4. So you can see this is just normal kind of media, but it's really interesting to see that there is some sort of crystal formation happening maybe on the outside of the media, not necessarily on it as much. And so here is that first square. A lot of carbon, there's a little bit of background, calcium, sulfur and oxygen, but nothing crazy. But if you hit one of those crystals, so if you hit crystal 4 or number 4 with the spectra, what you get is a bunch of these peaks. So this is looking a lot like calcium sulfate and maybe some silica. Don't know where the alumina would be coming from though. So, yeah, I think this is really interesting because at the ambient temperatures, it looks like we get precipitation not on the media. So we're probably not affecting the removal efficiency of the media as well, or very much. But when it's heated, it looks like the crystals preferentially precipitate on the actual media itself. So I guess in answering our second question, does GAC scale if exposed to level 2 at ambient temperature, is going to say no on that one. And so I guess to summarize, we're getting about maybe 15 to 20,000 bed volumes before we hit that 70 PPT level in our effluent. And I think a lot of these parameters can port over really easily to designing full-scale systems. And so I think the takeaway is we're probably going to have to put the GAC system in some sort of building. We don't have the infrastructure for that right now. We don't have a building that can accommodate that. So we're gonna have to figure out a way to squeeze that into our budget, but that's another hurdle. However, just when we felt like we kind of had our ducks in a row, we ran into a new hurdle in 2020, the year of surprises, if you will. And the surprise was that, there were discussions between the city of Alamogordo and the New Mexico Environment Department. And instead of having our discharge permit reflect a 70 ppt discharge level for PFAS, now the city wants zero non-detect. So if we were going to discharge any water to the city, we're not allowed to have any PFAS in it whatsoever. Some might call this ridiculous because I think even California at least gives you single digit numbers you can shoot for, which are extremely, extremely low, but at least not non-detect. So I think this is one of the instances where maybe regulations in New Mexico are more stringent than in California. Can't say that every day about everything. And so I think it just really makes life difficult. And so this, you could say this is fine, right? It's okay. We're gonna survive. And I do say this laughing because, Randy Shaw, who's the facility manager at BGNDRF, amazing guy. His perspective on this is really to turn lemons into lemonade. And, throughout this whole process, even as the constraints have kind of tightened on us, we've always managed to find a way through it. And as luck would have it, we actually have been developing business relationships with different entities to do R&D for removing PFAS. So it's actually kind of been a blessing in disguise. We've developed even stronger ties with NMED, even though our discharge permit's getting more stringent. We still have really, really good relationships with that, and they're excellent people to work with. So we're just going to kind of take this one in stride and overcome the challenge that's put in front of us. But just to illustrate what this means in terms of cost for us, really qualitatively, here's our 70 PPT line on the breakthrough, which was giving us our, if we had a full scale system, we could run 18,000 bed volumes. So, a few months or half a year on the same carbon. But now, if we do non-detect, which is somewhere around, I think 4 parts per trillion, has to be under 4 parts per trillion. What we're seeing is probably around 6,000 bed volumes is where our breakthrough is. So we're going from 18 to 6. So we're going to have to replace our carbon 3 times more frequently, which is not ideal, but I guess it is what it is. And so for our next steps, again, GAC, I think, is really the only game in town on removal for us, since, again, ion exchange is out of the question. And we're going to take the pilot columns that I had and scale them up to much larger ones. And so we've got an RFP out there for, I think, Calgon Applied and then AdEdge as well to build us quite a large, maybe a 50 GPM unit to handle a 50 GPM unit. I guess I'll just leave it at that. And so here's more of the making lemonade out of lemons. We've got a proposal that came through our DWPR program that we awarded, and I'll be working with Reza on this one, Reza Fudazi from NMSU, but they're also looking at removing PFAS from desalinated waters. And behind the scenes, I'm working with CDM Smith a little bit. They've got a novel technology called foam fractionation that is able to, I think, almost selectively get the PFAS out of salty water. So you get a really, really good volume reduction on that. And then you can treat the resulting water kind of as normal. And so, formed a lot of great partnerships through this, and I think it's just going to keep continuing. So many thanks to our team up in Denver, helping out on some of the technical things, Pei and Wenbin at NMSU for the analysis, as well as Dr. Patrick Stevens at RML and Golden, who also helped with some of the analysis, and then our operations assistant, Crystal Bing, she helped with a lot of the data. So that is all I had, and I'll take questions.
Let me start. This is Bruce.
Hey, Bruce.
Zach, you don't need to run your columns to breakthrough. If you do them in lead lag, you have the first column, you can run that to exhaustion. And the second is your polishing column. And then when the first column becomes exhausted, you move the second column up to the front. And so my guess is yes, a 4 PPT threshold will require more frequent replacement of the carbon, but it won't be the difference between 15 or 20,000 bed volumes and 4,000. You run it in lead lag, and then the second column will polish it to the 4.
Yeah, so that's part of the RFP that's out right now, or the RFI or whatever you call it, where we're going to have one of these companies kind of design based on our data, a larger system. But I guess one of my questions is always, how do you know what capacity you have in that lag system, right? If you're running it just to exhaustion and it's kind of catching the little bits and pieces coming out, you start to lose a bit of capacity there. Do you have any thoughts on that? I'm not really a GAC guy. I think Anthony Kennedy and the TSC is more involved with that, but haven't really gotten a solid answer on that yet.
You do the isotherms, you figure out what the isotherms is and are, and then you can use that to design your columns and make sure that your second column is big enough so that you don't get any breakthrough. And but it's pretty straightforward, I think.
Okay, I just didn't want it to turn into a guessing game where we're taking the first column and letting it go, to break through and just having it kind of trickle into the second one. And then over time, it's like, what's the capacity of the second one? And how do you even evaluate that? So, but good to hear your thoughts on that. Appreciate your input.
Zach, has the city of Alamogordo detected PFAS in their drinking water or even non-potable water sources like irrigation water? And if so, what is NMED requiring them to do in response?
That's a really good question. So I think they had really, really low concentrations in one of the wells out near the golf course in Alamogordo. I think it was below 10 PPT. It's just a monitoring requirement for them right now. So NMED hasn't laid the smackdown on them, if you will. But I believe it's coming, which is why I think they're putting pressure on us, is they see it as a risk where they might have a 0 PPT or non-detect discharge permit because quite a bit of the water is used for reuse. So they water, I think, the School of the Blinds and the parks, and then possibly the golf course with some of the treated effluent from the wastewater plant. So I think it's non-detects coming out of the wastewater plant, but with municipalities being pretty risk averse, I think if they see a point source of it, I can't really blame them for not wanting any of the PFAS discharge going to them if it's going to be reused in these public areas. So, but yeah, our hunch is the NMED is going to put regulations on them in the near future. So.
Zach, I also have a question. Thank you for acknowledge and Matthew's effort. It's such a great pleasure to work with you. So besides the GAC, I wonder if you consider using the less expensive adsorbents such as biochar. Right now, for some biochar products, their adsorption capacity can get closer to GAC, but the price could be lower. And another question is about the regeneration of the GAC, and if what PFAS would turn into. Can we completely remove PFAS from the GAC generated? Regenerated, sorry.
That's a good question, Pei. So I think we just started somewhere, and so we chose Calgon, the F400, because it's probably one of the more used carbons that's out there. So I think Phoenix put in a multi-million-dollar system. It was Tucson. Jeff Biggs out there gave a presentation on that not too long ago. They put a whole bunch of contactors out there for PFAS and I believe 1,4-dioxane. And then there's a bunch of other utilities that have used the Calgon F400. So there's a lot of empirical data on that. And I think just a lot of comfort knowing that it works. And so, you know, one of the benefits of BGNDRF is we're a research facility, so we get to do some research on this. And I'm kind of seeing the F400 as a baseline. And if we want to go out and start exploring different biochars and different media, it's going to give us a really good starting point to kind of compare. So not out of the question. We'll just need to carve out some time to do that. And then could you say the second part of your question? I'm sorry, I forget.
The regeneration of the exhausted or spent GAC.
Yeah, so that was not part of the study. In talks with Calgon, they say they offer a turnkey service. And so for $1 a pound, you can buy the carbon from them, and you can either do it yourself, or for $1.61 per pound, you can get the carbon and they'll drive it out and they'll suck out the old stuff and put in the new stuff and then dispose of the old stuff for you. My understanding is there's quite a lengthy process on Calgon's side for how they determine if carbon is acceptable for regeneration. And so we're actually kind of working with them on the side to send them some of the carbon we've been using, and they're going to determine if it's a candidate for regen. But so far it seems no. Some of the PFAS stuff I think they're starting to turn away from just because it doesn't regenerate as well. They have some studies out there that have shown that it actually increases the absorption capacity a little bit from some of these PFAS regens, but there's also studies out there that show when you do the high temperature regeneration in the furnaces, it just blows it up into the air. You make little ones out of big ones. They end up on the ground and back into the groundwater. So not sure what their game plan is for that, but I'm not really aware of too many technologies aside from plasma that can really actually mineralize PFAS.
Okay. Sounds good. And another question is about the pretreatment, because when you talk about the intermediate operation, because every time when you turn on the pump, there could be some clays or the sand coming to the filters, the GAC filters. I wonder, do you put a cartridge filter in front of it or no?
Yeah, we'll probably put a cartridge filter in front. We have cartridge filters in front of all the equipment and all the test bays now. So I just didn't show it on the diagram.
Okay.
Good point.
Yeah. Because the SEM XRD results, you found the aluminum, and the aluminum comes from aluminum silicate. That is a clay, comes from the sand, I think.
Okay. Maybe that is what we were seeing then.
Yeah. Okay. Sounds good. Thank you, Zach.
Thanks, Pei.
Very nice presentation.
That was great, Zach.
All righty. Well, thank you.
I'm going to reclaim the host.
Okay.
Wait, since it's quiet, let me offer an editorial comment, and I appreciate Zach's presentation. It was very good.